Can you do it?
I can.
Could you do it now? It'd be very good.
I'll see what I can do. Okay, so let's talk about the lab from Friday. So the whole purpose of how I wrote that lab was to force you to look at what's happening with acceleration relative to velocity, and can acceleration make you speed up? Can acceleration make you slow down? Can acceleration be negative? What does that mean? So here's the bigger picture. So first off, and I saw this with some labs in first block, make sure that your group defined the bottom of the ramp to be 0, okay? And the top of the ramp to be the 122, okay? And I explained that for some, but like some of the kids in first block made like 0 up here, and then it just screwed everything up. So make sure that you define 0 as being the bottom of the ramp. So here's the story. So you gave this card a push, okay? We didn't include the push. We started that analysis right after it left. By the way, start up yonder. Did you start the camera? Okay. So you're going to have this V1, okay? So here's the story. When you give it that initial velocity, when you look at it some point later on, there's only 3 options. It's either going faster, it's going slower, or it's going the exact same velocity. That's it. Well, only 3 things. That's it. So like, let's say, for example, you're driving to school. Mitchell was driving to school. And he looks and he's driving 40 miles per hour. Okay? 5 seconds later, only 1 of 3 things could happen. He's sped up to 41, he's slowed down to 39, or he's still at 40. That's it. Okay? Now, let me give you a hint. This big test on Friday is going to be a test on acceleration. So what do you think the velocity is going to be doing? Changing. Okay? It's going to be changing. Okay? Only unless I specifically, and I mean specifically, tell you to sit at a constant velocity. What are your only 2 options when it accelerates? It's going to
Slow down.
or speed up. Now, if it's slowing down, which direction are your acceleration vectors going to point? Same direction, opposite direction.
Opposite direction.
Opposite, and if it's speeding up, it's going in the.
Same direction.
That's it. Literally every problem you're going to have. Only 2 options that you've got: speed up, slow down, same direction, opposite direction. That's it. Now, clearly, as it goes up the ramp, what happens to the velocity? What does it do?
It slows down.
Slows down. So that's going to go to V2, boom, V3. Okay? So conceptually, the velocity vectors are getting smaller. So here's the story. If your velocity vectors are getting smaller, which direction do you think the acceleration vectors are pointing? Same direction, opposite direction? Opposite. So my acceleration vectors are going to be pointing down the hill. Now, here's the $1 million question. That's great. How can we determine the value of the acceleration? So there's a couple of ways I want you to be able to do this. And this is what's on the front of the lab. You have A equals V minus V naught over time. Okay? So this is the mathematical way of computating this. Right? So a lot of times what we'll do is that we'll look at this like in 2 different paths. We'll look at what's going to happen on the way up, and then we're going to look at what's going to happen on the way down. So Deacon, on the way up, I don't care about the numbers. On the way up, what do you know about the sign of the velocity? That initial velocity, is it positive or negative?
Positive.
Positive. When it gets to the top, it's going to change the direction, so what's the final velocity?
Once it stops, the final velocity is at 0.
0. Okay, so here's the story. So on your velocity time graph, it's going to start with some positive velocity. We don't know what it is. We don't care what it is at this point. We'll find it. We don't care at this point. And then that thing's going to go to 0. So here's there's 3 ways I want you to look at this. One is in terms of slope, you have a positive velocity that's going to 0. If you're in a math class, look, Etheridge, you're in a math class, what's the side of any slope that comes down like this?
Negative.
Negative. So at this point I go, oh, I have a negative velocity, I have a negative acceleration, positive velocity, therefore you have to be doing what? Speeding up or slowing down? Slowing down. Line's approaching 0 meters per second. Cool. Okay? That's one way to view this. Mathematically, if you look at this equation and you go, ooh, my final velocity is going to be 0. My initial velocity was some positive number, times the scalar quantity, time can't be negative. So I'd have 0 minus a positive number, I would get a negative acceleration that way. So here's the two different ways I want you to view this so far. Oh, I got a negative acceleration on the way up because I'm slowing down with positive velocity. Now here's one of the things I want you to understand. If I say, hey, is something slowing down, and you just say, yes, it is because it has negative acceleration, that's not enough. Well, does negative acceleration always mean that you slow down?
No.
No. Could you speed up with negative acceleration?
Yes.
So you need to put a caveat with that that says, oh, hey, this thing is slowing down because it has negative acceleration and positive velocity. Okay? You just can't say it's slowing down because it has negative acceleration. Okay? So here's the two ways you can view this so far. Mathematically, A equals V minus V naught over 9. I have 0 minus a positive number. I get a negative acceleration. The slope of my velocity time graph, which represents acceleration, Luke just said had a negative value. Okay, so that's the second way. The third way is in terms of vectors. Okay? You started off with some positive velocity. And that velocity vector got smaller and smaller and smaller. So therefore, the acceleration vectors have to point in the opposite direction. So that's the third way to view this. It says we have negative acceleration on the way up. Now, negative acceleration on the way up is not the problem. The acceleration on the way down is the problem. Because you bring with you, and I've discovered this over the years, you all have a bias towards associating negative acceleration with slowing down and positive acceleration with speeding up. You carry this bias, okay? And the purpose of this lab is to smash that bias, okay? Because here's the story. On the way down, you think, oh, it begins to speed up. Therefore, I should have positive acceleration because you have a bias towards thinking positive acceleration means that you speed up. Okay? And it can. Positive acceleration can also make you slow down. So here's the story. So on the way down, if you look at this velocity time graph, once you cross those 0 meters per second, do you still have the same negative acceleration? Yes. Why? Ms. Dozer, what does the slope of a velocity time graph give me?
Displacement?
Rhymes with acceleration.
What?
The slope of a velocity time graph.
Oh, the slope?
Yes.
Oh, acceleration.
Acceleration. Does this line have the same slope once it crosses 0?
Yes.
Okay. So mathematically, in terms of slope, it's still going to have a negative value. Cool. Now, on the way down, you go, Mr. Burkamp, I'm big into formulas. Happy for you. Okay? Now, on the way down, Thatcher, when that thing starts to go back down the hill, what's the initial velocity?
0.
0. What's the sign of the final velocity?
Positive. Oh wait, velocity negative.
Negative. Because you defined up as being positive, so now on the way down, it's that velocity vector is going to be pointing down the hill, right? Okay. So mathematically, on the way down, my final velocity is going to be a negative number. What's my initial velocity on the way down? So I'm going to have a negative number minus 0, which is also going to generate a negative acceleration. So mathematically, I get a negative acceleration. The slope of this graph says I get a negative acceleration. Okay? Now, in terms of vectors, Once you start down the hill, which direction Mac or my velocity vector is going to point? Up or down?
Down.
Are they going to get bigger?
Yes.
So which direction is my acceleration vector going to point?
Up. Down.
Down. Because it's going to be going in the same direction. Because it's going to be speeding it up. So here's the story. On your acceleration vectors on that page 2, okay, when you have this diagram, you should have 3 acceleration vectors on the way up and 3 acceleration vectors on the way down. If you want me to think that those acceleration vectors are getting bigger or smaller, you clearly draw them to show me that those acceleration vectors are getting bigger or smaller, okay? If you think they're the same length, you clearly draw them the same length, okay? Because I'm not, love y'all to death, but at 11 o'clock on tonight, when I'm cranky and I'm trying to grade that paper, I am not going to dig a ruler out and measure to see if those are exactly the same length or not. Oh, I don't know. No, okay? So if you want them to be the same length, you draw them the same length. If you think they're getting bigger or smaller, you clearly draw them so that I can see they're getting bigger or smaller. Thatcher,
Can we just like put congruent marks on them or something, so you can tell easier?
I can live with that. It's kind of a geometry nerd thing, but I'm hip to that.
Okay.
Yeah.
I'm trying to make his life easier.
Okay.
You're all doing it too.
Let me give you all a hint. No one in this class gets to call anybody else nerd. We're all nerds. Okay? Nobody, no, we're all nerds. And I'm good with that. Like birds of a feather flock together, nerds of a feather flock together. So, here's the nerd power. Okay. Let's talk about that last problem with the ball. So, your position time graph, oddly enough, should look something like this, and your velocity time graph should look something like this. Now, read the instructions. Yes, I said the R word, read. You should have a velocity here and a velocity here. That should be 1 second. That should be 2 seconds, okay? So here's the drill. Here's how you can check that you at least have a fighting chance that your answer is right. Find the area of this triangle. Take what you have as the height. Find the area of this triangle, 1/2 base times height. If the area of this triangle is 5 meters, you at least have a chance of being right. If you find the area of this and it's not 5 meters, I promise you it's wrong, okay? Because the ball went up to a height of 5 meters. So, there you go. Now, keep in mind, like many things in life, this is all about the process. If I look at that last problem and all I see are 6 answers over there with no work to justify them, bad things are going to happen. I'm going to snarkily write, really? Magic? No. Okay? So make sure that I see some work. Now, let me explain what's not showing work. Okay? That's not showing work. Great, you wrote down 5 halves. Cool. Nothing. Okay? Throw me a bone. Throw some units on it. Let me see what you're doing. Okay? Any questions on the lab? Mr. Hammond.
Do we use 1 second or 2 seconds when we're doing 26? Because it's going on the way up.
So, if you're gonna, I'll tell you this. Okay? So, and you're gonna throw this ball, from the time that you let go of it to the time that you catch it is 2 seconds.
Yeah.
So how long is it gonna take to reach its maximum height?
1 second.
So it's gonna spend 1 second going up and 1 second coming back down. Okay? Anything else? Charlie,
Could we go over 24?
what's
I'm just
24?
looking for like the right wording. It's just the velocity time graph has the same throughout this trip. Is that? I'm
So,
just trying to find like the right wording that you want.
let me give you a hint. It rhymes with lope.
Slope.
There you go.
I have.
Cause you copied me, is that what you're saying?
No,
Easy
I
thoughts,
took
don't get
inspiration.
judgy.
That's what happened.
Okay.
Inspiration from what you did.
All right, anything else on the lab? Going once? Twice? Sold. So get that handed in. So, Andrew, can you stop that camera?